Hello and welcome to Chapter 5, Laboratory Math. In this section, we're going to talk about some techniques that we can use to kind of calculate our different amounts of solutions and reagents and things like that, things that you might run into in a typical laboratory. To start off, we're going to go into percentages. So if you might need to make a reagent or a solution of a certain concentration, you'll probably need to use these equations to do that. The first situation that we're going to go over is a weight per volume concentration. So the equation that we use for that is our mass over our volume, and we'll multiply that by 100 to get our percentage. So why 100? Well, let's look into what percent means. So per cent, per means for each. So for every 100, you're going to have this much of this. So per and cent meaning 100. So for every 100. So for every 100 of this volume, you're going to have this much weight, or these many grams. So let's look at that in an actual equation. If we had 500, we needed 500 mils of a 50% NaCl solution. So we don't know what the grams are, so we're just going to put the mass up here. It's going to be our variable. Then we're going to put our volume here. So just 500 milliliters times 100 equals the concentration that we already know is 50%. And so we need to kind of move things around so that we can get this variable all by itself. So we might take our 100 and divide it over. So that's 50 divided by 100. That gives us 0.5. And then we're going to multiply this one because it's already divided here. So we're going to multiply that times 500. And that gives us 250 grams. We know that in order to make that solution, we will need 250 grams of NaCl, and we'll bring that up to 500 mils, and that will give us our 50% solution. So let's say that we made something, but we don't know what the concentration is. So let's say we had 50 mils of a solution, and we diluted it to, let's say, up to a liter, so that's 1,000 milliliters times 100, and that'll give us our concentration. So we just run that right through our calculator as is. So you want to put in 50 divided by 1,000 times 100. That gives you a 5% solution. Another problem that you might run into is that you have a certain amount of, let's say, grams of a reagent, and you know how much the concentration has to be, but you don't know how much to add to dilute that, how much volume you need. So let's say you had 25 grams of, let's just go with NaCl again, and we don't know how much the volume needs to be. 100 never changes because we're going by percent, so per 100. But we know that we need to make a 50% solution with that. So we're going to move some things around here. So we're going to multiply our V over to get it to the other side. And we're going to divide our 50% to get it to the other side. So the way I would do that is 25 grams times 100, because it's still here. And then divide that by our 50 that's coming over. That would give us 50 milliliters. So what happens if maybe in your laboratory or in a question, somebody puts the units into liters? Well, things get a little bit hairy. So you see, in this equation, you want that volume to be a bigger number than the mass, so your grams typically. So let's say you had 50 grams of NaCl in 1 liter. You took that times 100 and you wondered what's the concentration of that? Well, so let's try that. So that'd be 50 times 100. It'd be 5,000. And that's 5,000% concentration, which is it's not helpful, right? So my advice there is, if for some reason you got your units in liters, like I said, that might happen in a laboratory, then you're just going to multiply them by 1,000. That way you get it into milliliters, and it makes this bottom part bigger than the top. So if it's 1 liter, you just multiply that by 1,000. So that's 1,000 milliliters, which is the same thing. You're not cheating or anything here. You're just making the math work for you. So at that point, that's 50 divided by 1,000 times 100, 5%, which makes a lot more sense. Next kind of problem that you'll run into, either on an exam or in a laboratory, is a dilution of a solution that's already made up. So you have something that has a known amount of volume or known concentration, and you're trying to make something with a different volume and a different concentration from that same thing. So we're going to use a different equation for that. We're going to use V1P1 equals V2P2. What that stands for is volume of your first reagent, percentage of your first reagent, equals your second volume and your second percentage. So let's say that you need to make 40 mils. 40 because that's typically the volume of a Copeland jar. So you're going to see that one pretty often. About 40 mils of a 2% solution, let's say something like ferric chloride. And you have a 10% solution. So what is your V2 going to be? It's usually at this point that I like to look at the equation and make sure that everything's in the same units. With this equation, it's especially important that your units are the same. So if one thing's in liters, the other thing's going to be in liters. So in this case, we have a milliliters on our V1, so that means our V2 is also going to be in milliliters. So we're just going to move our 10% over to isolate our variable. So put that into your calculator as 40 times 2 and divide by that by 10. So that gives you 8 milliliters of that 10%. So what do you do with that information? You say, okay, I have 8 mils of a 10%, I need 40. So how are you going to finish that dilution? Well, you have 8 mils, you need 40. So you're just going to subtract to find out how much water you need to add to dilute that. So that comes out to 32. So you need 32 milliliters of water, which you're going to add your 8 mils to get your 2%, 40 mils of solution. So something that might happen in the laboratory is that you dilute something and maybe you go past what the recipe says, what your procedure says you should have done. So now you have a known volume and percentage and a known volume of the new solution, but you don't know what the dilution is now because you kind of fell off the procedure. Maybe you diluted it too much. So now you're going to try and figure out how much is in there now. What's the actual concentration, and see if maybe you can salvage that. So let's say you started with 40 mils of a 10% solution, and you diluted it. Maybe you're trying to go to 50 and you went up to 60 mils. And you don't know what the concentration is. So we're just going to do that same thing. We're going to move that 60 over here. That's 40 times 10 divided by 60. That gives you about a 6.67% is what you've diluted it to. So now you know. Maybe you can take that to your manager or somebody who knows to see if maybe that still works with your procedure, or if maybe you just need to start over. Another thing we may need to calculate in the laboratory is the gravimetric factor. What a gravimetric factor allows us to do is to take an old formula with an old concentration of dye and use the new dye that might have a different concentration to make the same quality and the same concentration of dye in the new stuff. So, for example, maybe we need to make about 60 mils of a dye. Let's say it's a 1% dye. Let's say maybe like an Alshan blue or something. And the stuff we always used up until now had an 80% concentration. So our Alshan blue dye had an 80% concentration up until now, and our new one has a 60% concentration. So obviously we can't use the same stuff that we used to, because if you put that 60% dye with the same amount that we used to put in it, then it'd be too dilute. And so we kind of have to correct for that, and the gravimetric factor allows us to do that. The thing we want to do is look at our procedure, or in this case, we're going to figure out what the old procedure was. So we're going to use our old weight per volume calculation. So we don't know what the weight is, but we do know the volume that we want is 60 milliliters. So we don't know what the mass is, times 100 equals 1%. So what we're going to do then is divide by our 100 and then multiply by our 60, and that'll tell us how many grams that we used to use to get that concentration. So we do 1 divided by 100 times 60. That gives us 0.6 grams. That's what we used to use. What do we do now that we have this new concentration? What we'll do is we'll take the one that we used to use and divide by the one that we're going to use now. So that's just 80 divided by 60, which equals 1.33 repeating, so 1.33. So that means that we're going to need 1.3 times the amount of the new stuff in order to get the same concentration that we had with the old stuff. So that is our gravimetric factor right there. So in order to make this new dye with the procedure that we were using before, we used to use 6 grams to get that. But now we're going to take that 1.33 times our 0.6 grams, and that'll tell us how many grams we need to use now. So put that into our calculators as 1.33 times 0.6. So now we need 0.798 grams of this new stuff, which makes sense. It's a lower concentration, so you're going to need a little bit more of it to get that same dye concentration. Next thing that we're going to cover is molarity and normality. And now, with this, there's a lot of chemistry that goes into it. So I'm going to try to cover some of the chemistry background for those of you who haven't done molarity and normality, or maybe haven't done it in a long time. Though it's going to be not so deep that we're going to spend a few hours on it. So just try to follow along, and I'll try to make sure that all the prerequisites are there and make it a little bit easier for us to review or learn it for the first time. So when we look at something on a periodic table, let's say chlorine, you're usually going to have your atomic number around here, and then right around here you're going to have this number typically with some sort of decimal. And for chlorine, that's 35.453. So what is that number? That is its atomic mass. And so you can think of this as grams per mole. Now what is a mole? Well, a mole is kind of a way of counting the atoms in something. So when we say that chlorine's atomic mass is 35.453 grams per mole, that means that 1 mole of it weighs that many grams. So a mole by itself is the weight of a specific number of atoms of that element. So let's say with chlorine. So in chlorine, 1 mole weighs 35.453 grams, and 1 mole is a number of atoms, and the number of atoms that we pick for everything in order to standardize it is Avogadro's number. You don't have to remember that, but it's 6.02 times 10 to the 23rd, which is just a really big number. That's a bunch of atoms. So this number of atoms of chlorine is 1 mole, and it weighs this much. So this many atoms of chlorine weighs this much, weighs 35.453 grams. If that wasn't confusing enough, typically when you're working with molarity or normality, you're going to see something like this. So notice that is an uppercase M. So that does not mean 3 moles. That means 3 molar. So what does that mean? So molarity is measured in moles per liter. So in this case, this has 3 moles for every liter. So in 1 liter of solution, it will have 3 moles if it is 3 molar. Same if it was 5 molar, then you would have 5 moles of something for every liter of solution. So how would we make something like that? Let's say we wanted a 3 molar, let's just say NaCl. Let's make some table salt. So what we have to do is find the molar mass of those things first. So NaCl has a molar mass of 23. Chlorine has the molar mass of 35.453. So if we add those together, it'll tell us how much 1 mole weighs. So how many grams of NaCl we need in order to get 1 mole, or a 1 molar solution. So we get 23 plus 35.453. That gives us 58.453. So that would give us a 1 molar solution, but we need a 3 molar solution. So this should be pretty easy. We're just going to take that 58.453 and multiply it by 3. And that gives us 175.359 grams. And what that represents is how much sodium chloride by weight we would have to add to 1 liter, or actually dilute up to 1 liter of solution to get a 3 molar solution. Well, let's take this a step further. Now we're going to pick an element here that's a little bit easier to work with. So let's just go with oxygen. So oxygen has a molar mass of about 16. We'll just round it up to 16. So the thing with oxygen, though, is when it's out in the open, it's an O2. It's 2 oxygens together. So effectively meaning that its molar mass when it's actually out and about is about 32. So you have to remember that when we're doing this, because if we wanted to prepare something, let's say a 3 molar solution of oxygen, well, there's always going to be 2 together there. Not only do we have to worry about that, but also you're going to make a certain volume of this. So let's say 1 liter. So in order to work all of that out, there is an equation we can use. So we can use our weight in grams equals our molarity times our volume. It has to be in liters. It's important because the units of molarity are in moles per liter, times your formula weight. And formula weight is just that weight that we found with oxygen. So it's the weight of what you have given what its actual state is. So in this case, oxygen tends to be in O2. So you would take that molar mass and times by 2, because in the formula there are 2 oxygens. So let's just work this out to see how many grams of oxygen we would need for our solution. We want a 3 molar. We want 1 liter of it. And the formula weight is 32. So 3 times 1 times 32. Go ahead and put that in your calculator. Is 96 grams. We need 96 grams of oxygen in order to get that solution. Thing to keep in mind, as we said, the units all have to kind of match up. So if somebody says, well, I need 500 milliliters of something at a given molarity, so let's say the same problem, in that case, we would just convert that. So 500 milliliters is 0.5 liters. So in this case, where we start out with milliliters and try and go to liters, we're actually going to divide by 1,000 rather than multiply like we did before. So in this case, that would be 0.5 liters, and you would just run that through, and that would tell you how much you need. Now, another thing you might encounter is normality, where something needs to be a certain normal. So it might be expressed as 1 normal, like that. Now, the only difference with this is it's like molarity, but with 1 extra step, or 1 extra thing added to the equation here. So we have our normal equation with grams equals our normality, instead of molarity, times our volume, times our formula weight, divided by positive valence. What positive valence is it's the number of dissociable or replaceable hydrogen ions, and it's kind of something that it's a big discussion. A lot of things can be looked up, and that's what I would recommend. If this is something you have to do off the cuff in the laboratory, then look up how many dissociable ions are in the things that you're working with. Next thing that we're going to look at is temperature calculations. These are fairly simple. It's mostly just memorization of a couple of formulas. So if you have Fahrenheit and you're trying to find Celsius, then you're going to use this equation. There's a couple of permutations out there that you can use, but this one I find is a little bit easier to remember. So it's just your degrees in Fahrenheit minus 32, and in parentheses, so you do that first, and then you multiply that by 0.0555. Now, if you have Celsius and you're looking for Fahrenheit, then you would do this one, which is your degrees in Celsius times 1.8 plus 32. And like I said, you probably could just memorize one of them and try to backtrack them if you got something that wasn't the one you memorized, so to kind of do the algebra and figure out the other equation. But honestly, it's just kind of easier for me to memorize both of these going into the test, the exam, or just kind of post both of these in a laboratory if it's a conversion that you have to do pretty often. Let's run through an example. Let's just look at the freezing point of water. So if we want to know what that was in Celsius, so we're going to do 32 degrees Fahrenheit. So our answer equals 32. That's minus 32 times 0.0555. This makes, obviously these make 0 times 0 equals 0 degrees Celsius. So what if we went the other way around? So freezing point of water is also 0 degrees Celsius. Let's put it into the other equation. So that would equal 0 times 1.8 plus 32. So we're going to do these first, and that equals 0. So 0 plus 32 equals 32 degrees Fahrenheit. That about does it for lab math. we should reach the end of chapter 5. So we kind of covered how to do each of these problems, did a couple of examples, but maybe you need more examples, or maybe you'd like some step-by-step help. In that case, I would get a hold of somebody like myself. Doing lab math with a tutor present is a lot more effective, I find. But after watching this lecture, you should have enough to kind of get an idea of how to do it. And you probably want to refine that with somebody, like I said, with some private tutoring. Our next chapter is going to be on nuclear and cytoplasmic staining. And in that one, we're going to kind of color together as we go through how nuclear staining works and looking at kind of the layers of staining and how that happens. So I look forward to seeing you then. Have a great one.